Okay. We are continuing down our path where you are getting some computer programming basics through the book and just practicing some trivial stuff. We'll get into writing more complex code here in class soon enough, but right now we're still learning about this dude that we want to be able to boss around, and we got to understand how he works, right? Um, know your enemy, I guess, is the thing. So we've been talking about all these different conversion things, and actually, what did you have to for those of you who were at CS Club last night? There was some scavenger hunt. Didn't you have to convert something? What were you converting? I heard him saying something about ASCII or something, but I was playing Dungeons and Dragons. You don't even remember? Oh, I got you. So you had to do. I got you. Okay. But so you had a little background in it from what we've been doing? Good. I don't know. That scavenger hunt seems stupid to me. Was it stupid? The scavenger hunt that they did at CS Club yesterday. I was looking for the cake. Dry campuses, come on. All right. So we've been talking about these different bases and things like that. And we hopefully understand that numbers aren't just for math. We can use them to map to different things. We've talked about ASCII, talked about Unicode. Um, Remind me, what's the difference between ASCII and Unicode? Definitely one's older. Which one's older? ASCII's older. Okay, and what's their difference? Do ASCII versus Unicode. This, this is a good thing to go back to. It really isn't that important that you know exactly uh, the details behind this, but this gives us a good example of why we might use different bases or different sizes of values. So ASCII is a 7-bit character set. Now, technically, you have extended ASCII, which is what we actually call ASCII now. And this is 8-bit character set. So for all intents and purposes, this doesn't actually exist. Nobody thinks of ASCII as 7 bits anymore. We made it 8 bits. We added all the smiley faces and playing cards and all these different symbols that existed way before we had graphics. You know, when you were just running your poker game in DOS or something. Um, Unicode is 16-bit character set. What does that mean? What's the difference between an 8-bit character set and a 16-bit character set? Go ahead. Yeah. Number of characters we can uniquely represent, right? So with an 8-bit, so how many unique characters can be represented in a 8-bit character set? What do you think? 258. 258? Close. Further away. 256. But why is it 256? Yeah, 2 to the 8th power. Yeah, so it's not necessarily like memorizing some random number. It's a power of 2. You're going to see a lot of things that are powers of 2 in computers. Why are things powers of 2 in computers? Zeros or ones. All comes back to binary. All right, so this is 2 to the 8th power, which is 256 unique characters that can be mapped using ASCII. All right, we're going to come back to this in a second. So that must mean that for Unicode, how many characters do we have? How many unique characters can we represent? 2 to the what power? 2 to the 16th power, which is 65,536 unique, 536 unique characters.
So the main difference.
It represents more characters, which means that we aren't just representing English and smiley faces. We now have all these other languages. You know that the world speaks more than just English?
What?
Yeah, I know. I don't think it makes sense either. It's crazy. Um, so especially what ASCII is the American Standard Code for Information Interchange. So it's right there in the name, I suppose. But anyways, we have 65,536 unique characters that live in the Unicode character set. So we get way more characters. We've gone from 256 to 65,536, and it just cost us an extra byte of memory. It's a that's a cost, but it's not that much by today's standards, right? Did I already talk about cost of RAM and stuff? What it cost to upgrade 8 megabytes of RAM on my computer years ago? Yeah, it used to be super expensive, and that was after memory had come down in price. So when we think about 8 bits today, that seems like nothing. It's not a whole bunch of memory since most of your computers have 16 gigabytes of RAM in it, or 32 gigabytes of RAM. Not bits, bytes. So today, memory is not really a problem, although it's becoming a problem again with AI. We're using a lot more memory and a lot more computation power again. So we're kind of doing this throwback to what computing was like in the maybe 70s and 80s. In reality, it's 8. When it first came out, it was 7 bits. They just didn't use all 8 bits. They had 128 unique characters originally that they just said, we have an extra bit to work with because the smallest data type that any programming language supports is a byte, which is 8 bits. So you're already using 8 bits of memory, even if you're only choosing to map 7 of those bits to stuff. So they say, we get an extra 128 characters for that extra bit that we're already using. Let's find stuff to put in there. So if you go and look at extended ASCII, you will see, legitimately smiley faces, weird symbols, a lot of playing cards, because this came out way before we had graphical user interfaces. This is when people were writing for things for the Commodore 64, all text-based card games and stuff like that. So that was our graphics. Let me go here. Signed versus unsigned. Actually, let me do something else here first. Let's call this data types. All right, so first day of class, I mentioned that computer programming is the skill, the language doesn't matter. So you guys are messing around with Python right now because it's the current cool kid in languages, and I'm actually not necessarily a huge fan, but I use Python all the time because I do a lot of AI stuff, and all the libraries are built into Python for that, so you'd be stupid not to. But you're messing around with a lot of very new technology. Python's been around for a while, but you're doing your homework assignments using Python inside of Google's version of a Jupyter notebook, which is kind of the current cool kid thing to do, especially when you get into data science and stuff like that, but anything AI. So in this class, you have, how many of you are computer science majors in here? All right, and we have probably a couple of business analytics majors. All right, so, those two worlds are kind of coming back together. So all of the computer science people, when you go out in industry, you're going to be doing AI stuff. You'll still be doing coding stuff, but AI is going to be in everything moving forward, right? And business analytics is effectively the business side of AI. So yes, you're doing AI stuff, you're doing machine learning, but most of what you're doing is you're visualizing data. Whereas the computer science side might be more of the training models and stuff like that, but you're using similar tools. So you'll very likely be using Python for a lot of AI related projects. Jupyter notebooks might not be what you use for production stuff, and I'm going to show you coding examples in other environments here, but Jupyter notebooks are a good way for you to kind of work on your things in a single document, but in sections and put little notes next to it and stuff like that. This is what this is doing and that kind of stuff. So it's kind of good for learning. Plus, it is a tool you'll be interacting with teams when you're in industry, even though it might not be when you sit down to actually write software, your main development thing. It's more of a note-taking type tool. And hopefully what you're seeing there is they've decided, and this is super popular, they've decided with Jupyter Notebooks and Google Colab that sometimes it makes sense when you're trying to take notes or represent stuff to just write code to accomplish something. Sometimes writing a little computer program to visualize something or do something is actually faster than using like a spreadsheet or something like that. That's the skill set you're trying to build up, where programming isn't something that takes you a month to do. When you start coding, it's going to be difficult. You're not going to be very good at it. You're going to make a lot of mistakes, all this stuff. But eventually, once you get over that, get over that time period, you'll look at coding as like, oh, I can just write a quick program that just does this. Jupyter notebooks are a good place to do that. But now, getting back to that idea that programming is a skill set, the language doesn't matter. What I'm going to show you here is pretty much what all programming languages have, or a very close subset of this. So we talked, let me throw another slide in here. I might even have it somewhere else in here, but let me just throw it again. We talked about low-level languages, machine language, and high-level languages. So every programming language falls into one of those three categories. Every programming language also falls into either the category of strongly typed or loosely typed. Did we talk about that? Okay. So I'll just throw it. Well, if we already talked about it, I won't put it in there a second time. Okay. Yeah, I mean, it's somewhat unimportant. It just is related to this. So that kind of comes back to this idea. If you're going out, we're dealing with variables here when we talk about data types, the kinds of things that a computer program can remember. So what we're trying to move towards is this idea of how do human beings solve problems? We remember stuff, we ask questions, and we do repetition. Those are the things that we do to solve problems. And every single programming language gives us facilities for doing those things. When we talk about data types, what we're really talking about is what kind of stuff can we remember in our programs? Creating a little variable, associating it with a value. What are the different kinds of values I can hold? So numbers, characters, strings, Booleans, we'll talk about those, floats, decimal point kind of values. So let me list all these. So we're going to go back in time a little bit and talk about some earlier programming languages. If you were to look at this hierarchy of programming languages over the years, draw some pictures here. Now, while this isn't necessarily the very first programming language or anything, let's say that the language I'm about to put up here is the first language that means anything, that matters in a modern computer programmer's world. It's a language called C. All right. There are three kinds of programming languages. So this is coming at this from another angle. Just as there are two kinds of programming languages, loosely typed, strongly typed, just as there are three different kinds of programming languages, machine language, low level, high level, we also have three kinds of programming languages, which are procedural, object-oriented. We've heard that word, right? That phrase, whether you know what it means or not, is a whole other story, but we've heard of object-oriented code, or OOP. And then functional. We're going to kind of skip functional right now. I'll give you a couple of examples of this. Lisp, Haskell, Scheme, which is a superset of Lisp. We use that in the language theory course, where we teach you how to write a programming language. I used to teach that class, but I taught Professor Blade when he took that class. So now he teaches that class. I teach the graduate version of that. But just throw functional languages, in the back burner somewhere and come back to it next year or something like that. Let's focus on procedural versus object-oriented for us here. I'm going to give some definition to that here in a second. So C is a procedural language. C++ is object-oriented. This is incredibly poor spacing, but whatever. There we go. All right, so let's talk about what the difference between these things are other than just words. So we're going to say procedural languages are older. Our original programming languages were procedural languages. So these tend to be one giant document with, let's just say, that is difficult to read because everything is in a single place. Think of this like you have a garage and you have it organized where you know where everything is. But to another person, they walk in and they say, "What is this mess?" Right? Just a pile of stuff. And I like to describe this from the perspective of a telephone, even though that starts losing some of its shine today, because how many of you have ever actually used a regular telephone? The dial tone ones? Or the manual twisty things. They used to be attached to the wall too. You couldn't move very far. But let's pretend for a second that I've brought in a telephone for show and tell. And I'm going to bring this giant pile of wires and throw it here on the table. And I'm going to say that is a telephone. Now, at first, you might look at it and say, "Yeah, I don't believe you. That's just a pile of wires." Now you come up here, you start messing with it, you find the headset, you hear a dial tone, whatever, you see some buttons or the spinny thing. It's like, okay, you convinced me that's a telephone. Didn't look like a telephone, but it was a telephone. Okay, that is a procedural telephone. That is the procedural programming language version of a telephone. We see all the details in all of its glory just hanging out all the time. All right. Even though, how many of those wires, when you use a telephone, how many of those wires do you actually have to mess with? Very few, right? So when we think about a telephone, whether it's your smartphone or whatever, you have these public interfaces, the parts of it that you interact with. Yet you know that inside that case is a whole bunch of difficult stuff, electronics and things like that, that some smart person put together and it all works and stuff, and you're just never going to touch it again. Right? It's hidden in there. You know it's there. It's an important part of what makes that thing work, but it's hidden. That's the object-oriented version of a telephone. It's organization. All right. So if we say procedural telephone, big pile of wires that upon investigation is a phone.
So like the difference would be just the like complexity, like
all the complexity is there. I mean, if I take my phone out and I put it next to that pile of wires, so look what we're going to imagine. There's the pile of wires over here. The complexity exists in both of them, right? The same stuff is in both of them. This one just looks like a phone. So it's Tupperware. The difference between a procedural language and an object-oriented language is effectively Tupperware. It's containers. We've taken all the ugly stuff we don't need to deal with and we've shoved it inside this little box. And then we've poked little holes here So we got some volume controls here, and we have this other magical button that Apple decided, I think, is to compete with Samsung. Then we got the stupid camera flippy deal that nobody asked for. But in any case, we have some external interfaces that actually are giving us ways of clicking on stuff, but most of the details are inside of this. This is the object-oriented telephone. The pile of wires is the procedural version of telephone. All of the same stuff is there. This one's just put inside of a nice, pretty looking box. Make sense? All right. So object-oriented programming languages really are not that different from procedural languages other than they give you some tools for organizing things. That's it. Same logic exists. You could build the same things. So we can say has containers to hide details that are important but not used often or something like that. The object-oriented telephone looks like a phone where all the wires are hidden on the inside and only the public interfaces are available to the user.
So when you just say object oriented, languages are more up to date.
I mean,
Or
they're definitely newer. They're definitely newer, but this kind of comes down to what kind of tools do you use when you clean your room? You know, do you put stuff inside of organizer things? Or you just kind of tidy things up into 3 or 4 piles? You know, the 3 or 4 piles might be your procedural version of cleaning your room, but then all of a sudden everybody and their brother came out with all these, you know, we have a whole store, the Container Store. My wife's like a corporate member of the Container Store. She just buys these containers left and right. We have so many containers, they have labels on it. She has containers inside of containers. It's a problem. We're having her checked. So yes, it's more modern, but it really isn't a complex thing. It's put stuff in buckets so we don't have to look at the wires. That's at the end of the day, that's what it does. So then the question would be, why did we, when we had procedural languages, let's say we didn't know any better. And remember, we go back to the beginning of this course, and I mentioned that human beings are really good problem solvers. Programming languages are our way of telling a computer what to do. So it has to give us the tools that we need to boss this thing around. It has to give us the tools that we need to solve the problems that we want to use a computer to solve. Would you guess that in the very early days of computing, we were solving easier problems than we're using computers to solve today? Some of it is because the computers didn't have enough power to do it, or there wasn't enough memory, or human beings hadn't, invented new ways of using computers to solve different problems. So we started off with these kind of monolithic old procedural languages that got the job done, but it didn't necessarily look pretty. But our programs back then were relatively small enough that it wasn't a big deal. But then as they got larger and larger and larger, and the wires started to become a problem, that's when we said, you know what, we probably need to do something about this. And that's where object-oriented languages came from. How many of you have heard of C++? All right, so C++ is the object-oriented version of C. Now I'm going to show you another language here. Objective, hey. C, go with that. How many of you have heard of Objective-C? What can you tell me about Objective-C and or C++?
C++ is like, I mean, I don't really know much about it. It's like slightly Java.
Well, Java is a lot newer, so we can put Java down a level here. We'll get it on here in a second. Everybody used C in the early days. But then we had a couple of companies that became big players in computing. They hated each other, right? Microsoft and Apple. Microsoft had a product called Visual Studio with Visual C++. So Microsoft decided to adopt C++ as their object-oriented programming language. Well, because Microsoft adopted it, Apple wasn't going to use it, right? So Apple's version of object-oriented C was called Objective-C. It still looks like C. Actually, I like Objective-C better than C++. At some point, I'll show an example of why I like it, kind of for the same reason that I dislike Python. So at some point, I'll have an opportunity to display that, but whatever. So in any case, what we're seeing here, this divide, is two companies that hated each other, created the need for these two languages, which basically are the same thing. If you were to write iPhone apps the day the iPhone App Store went live, you would be writing in an Objective-C using a library called Cocoa. Actually, it was Cocoa Touch for the iPhone, for the touch interface. All right, so then from here, we got Java. So in the early days of Java, people would call it C++++, something like that. Java is still object-oriented, tries to solve some of the, let's call them quirks with C++. Part of that is going to be memory. We're going to be talking about memory today. This kind of goes back. I code in Java way more often than I code in C++, but I like C++ better because you get to directly work with memory. And pointers are important, and as computer scientists, you need to understand memory. And hopefully in here, we're going to keep driving that point home when we talk about bits and bytes and conversions. And today we're going to talk about how RAM works and why hexadecimal is even a thing and all this stuff. But, in any case, Java became a little bit more developer friendly. And maybe we can just kind of pigeonhole that and say, there are some things in C++ where 100% of programs written in C++ maybe start with the same two lines at the beginning and end with the same line at the end. And Java just said, if you're always writing these three lines, why don't we just automate that for you? So we'll hide them, but trust us, it's still there. So Java tends to hide stuff from you that is still there. It's a convenience. It's like a power tool. Okay. It's great once you've learned a program. Java is a fun language to code with because it takes some of the monotony from C++ out. So anybody know who made Java? These are old tech wars. We're watching the life and death of tech companies as these languages evolve. So Java was made by a company called Sun Microsystems. Microsystems. How many of you have heard of Sun Microsystems? They used to be in the server space. They would, a lot of companies that ran Unix servers, they were running a version of Unix called Sun Solaris. Famous. They used to have servers called Spark stations that had their own computer architecture, their own stuff. You can go out and still look at Sun Spark Systems or whatever. Sun Microsystems actually is still around. You just pronounce their name differently. You pronounce it Oracle. Oracle absorbed Sun Microsystems. All right. So if you go to a web page, if I say java.sun.com, it takes me to Oracle's Java programming language site. Sun Microsystems was a publicly traded company. Guess what their ticker symbol was? Not Sun. Java. So their ticker, they invented Java, but never figured out how to monetize it. Oracle, no, Oracle bought the company. Microsoft tried to steal it. That's where our next thing comes in. So, yeah, of course. How many of you have heard of a programming language called C Sharp? Okay. So what happened? Microsoft tried to steal Java. In their Visual Studio product, they had a language called J++, which was their version of Java. And let me dive into this a little bit here. Anybody know what the JVM is? What is that?
Java
virtual machine.
Java virtual machine. Okay, and what is that? You know anything about it?
Where wasn't the point of Java was trying to make it to where it's like write it once and it runs everywhere. The virtual machine is what is written for different operating systems, and then Java runs the same on all of them.
100%.
At least that was the goal.
Yeah, it's the reason why Java is so special. It's also why Java sucks, depending on what you're using it for. So JVM, this is the Java virtual machine. Okay, we're still kind of learning about this history. So let's put this back in the mid 90s, 1995, 1996, something like that. How many people, what percent of computer users in 1996 do you think were running Windows versus running Mac OS?
Probably 5% for Mac.
Oh, they wish it was that high, but we could say that's reasonable. 95% Windows, 5% Mac. It's probably more like 98% Windows, and the other 2% was Mac and Linux. Okay, so a very small percentage of users were running Mac OS. Now, if you are somebody writing video games or software of any kind, but usually it was video games, which kind of led to this problem. If you're writing a video game and you have to write it for two different operating systems, right? We've already looked at like the Hello World assembly language code, and we talked about it having power tools where it actually leveraged the Linux operating system, which means that if you were to write Hello World to run on Windows, that assembly code would actually be leveraging the Windows operating system calls, which is different code. So it would have to be recompiled at the very least, probably written a little differently regardless. Same thing, go over to Mac, especially back then, they were running PowerPC processors. Now they run then they ran Intel, then they went back to their own processors after they bought a processor company. But in any case, if you're somebody writing video games, you would probably write your game for the platform that most people are running, right? Windows. Same thing's true today. If very, 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 very few games come out for Mac only. Maybe even none, but a tiny, tiny bit of things come out for Mac only. Usually it's Windows, and if you're lucky, they port it to Mac if the game was popular enough, like World of Warcraft, that kind of crap, Overwatch. But in any case, if you would put those two groups of people in a room, the 95% and the 5%, 98% and the 2%, and let them complain about the software that they don't have access to, do you think the Mac people probably made a disproportionately loud noise? Absolutely. You go into the Apple store, they pointing you to the Kool-Aid over in the corner somewhere, right? So Apple people complain loudly. And so really Java was a programming language to kind of answer a problem that wasn't really a problem. This idea of write once, run anywhere. So this had a write once, run anywhere. This means we write our program in Java and it will run on any computer that has the JVM. So rather than you having to write your program for Mac and then you write your program for Windows and you write your program for Linux, maybe with small changes, maybe with big changes, maybe it's just a recompile, which we'll talk about that too, but it's not just straightforward. Rather than having to do that, you can just write it in Java. And what Sun Microsystems did is they wrote the Java virtual machine for Windows. They wrote the Java virtual machine for Mac. They wrote the Java virtual machine for Linux. The Java virtual machine understands Java. All right. So your Java program will run on any computer that has a Java virtual machine. Now, that doesn't mean the performance is always going to be identical. Maybe there's certain things that are a little bit more efficient on Windows or on Mac or on Linux. So, but technically your program would still work. It just might be a little slower for very specific things on certain platforms or whatever. Okay. So this was good theoretically, let's say. Sounds great on paper, even though it was solving a problem that really wasn't a problem. Make some sense? But in any case, Microsoft comes out and they come out with the Microsoft JVM, their own Java virtual machine that runs specifically on Windows. And it was considered to be a higher performance virtual machine for Windows since Microsoft has access to the internal little tricks and stuff like that. Go ahead. Oh, because they wanted to steal the software. Yeah. Yeah, because they came out with a language called J++, which was Java syntax that ran on Microsoft's Java virtual machine. This is just what they do. And it's not, I mean, it's not even demonizing Microsoft. They're all evil, right? This is what these big companies do. It's kind of why these app stores and stuff have been such a big deal for independent software developers. Because in the past, what would happen, and it still happens today for, let's call it game-changing type applications. But, let's assume back in the, we saw it when we talked about Microsoft's deal to sell IBM or to license DOS to IBM. They didn't have DOS. They didn't have an operating system. So they went out and bought the operating system. But let's say you're some guy who writes some really cool software in your, at home. You don't have the resources that Microsoft has to market that, get it in all the stores. Because before we could just download stuff online, you had to have your software on the shelf at Best Buy. You used to walk up and down the software aisle like it was a bookstore. All right. So to get it into stores like that was not easy. Independent software developers really couldn't do it. Where now you don't even have to put pants on to get your app on the App Store, right? You just upload it, pay them $100 a year, and you got apps. But in any case, the way it used to work is if you came out with something really, really, really cool that you weren't going to be able to make money off of at the same level as a big company could, you probably were sitting there figuring out how to monetize it, not being able to do it. Microsoft would come in, steal it from you. You would then threaten to sue them, but you don't have the money to sue Microsoft. They would settle with you outside of court, give you your $1 million or whatever. And then they would go and make zillions of dollars off the software that they stole from you that you probably wouldn't have been able to make that kind of money with on your own. The world keeps going around. Everybody's happy. Somebody walks up and says, hey, that thing you wrote at the hackathon, I'll give you $1 million for it. You say yes, right? That's how these big companies tend to do business because it's faster for them to get that product to just steal it and settle outside the court than to negotiate with you to buy it. It's just, I don't know, call it capitalism. So anyways, but this was kind of an interesting example of that. So Microsoft basically tried to do a hostile takeover of Java and was trying to make it their own language because Microsoft was still the cool kid. Everybody wanted to run Microsoft stuff or whatever. But Sun Microsystems wasn't just some kid writing code out of his grandma's basement. This is a legitimate big company. Not quite Microsoft big, but like kind of almost. So Sun Microsystems turned around and sued Microsoft and won. Several things happened as a result of this. How many of you have heard of Bill Gates? Yeah, he stepped down as chairman of Microsoft. The result of this lawsuit is when that happened.
Oh.
Yeah, it was part of the deal. So then one of the other founders of Microsoft stepped in, Steve Ballmer, who was in that same meeting with IBM, and he took over Microsoft for a while. Then I think you had the Internet Explorer debacle, where they were forcing it on every machine, and that was apparently a monopoly or whatever, and somebody had to pay somebody zillions of dollars, and then he stepped down.
So they literally so they steal, get sued, and then the person who's.
Well, that just happened to be part of this deal. But what ended up happening from our perspective, this is more of the politics behind it, but from our perspective, what happened is Microsoft tried to steal it. Sun Microsystems sued them. Sun Microsystems won, and Microsoft could no longer have a J++. They couldn't have their own Java virtual machine. So they weren't allowed to do that. They were going to have to go make their own language. And they introduced this language in maybe 2000 at the University of Illinois in Urbana-Champaign at the ACM conference. So I was at that ACM conference. I was sitting in it. The classroom was smaller than this room where C# was originally announced. And everybody goes to the Microsoft presentations at these things because Microsoft gives away the best free stuff. You go to the other places, they're handing out little bouncy balls. Microsoft was giving out boxes of Visual Studio 6.0, which is like a $600 software. That they were giving out the student version, but we had all pirated it at that point. so that went on eBay. eBay was like a week old back then. Well, I mean, he helped me do it. It was on BitTorrent ahead of its days. So allegedly. So in any case, I'm sitting there, and had been a big Java developer. I'd been writing Java code since Java came out. And so I'm sitting there, and they're announcing, oh, this is what we built C# from the ground up, brand new language, best thing since sliced bread, yada, yada. They're describing Java. But technically, the syntax is a little bit different. And it still looks like C++, which looks like C because all these languages came from that. And what did they do? They're saying, oh, we did this. They're just describing it to me. And then here's the kicker. We said this piece up here for the Java virtual machine, we write this once and run it anywhere. So any computer that has the Java virtual machine can run any Java program. So this was kind of a big selling point for Java, even though it didn't really solve the problem. Nobody writes video games, like big video games in Java. The performance isn't there for that. You could write, yeah, I mean, but big games. Minecraft is a very popular game. That doesn't mean it's a super complex game, right? So, I mean, you could make Angry Birds in Java. These are games that don't require, like, you don't go out and buy a $4,000 GPU to play Minecraft.
You shaders.
You still don't need the $4,000 one. You can.
I was asking my teacher, and she was just like, "Oh, well, they made Minecraft," and I was like, "I'm not gonna make it."
Minecraft came way after Java.
But I'm just trying to figure out what.
Yep,
the point of
we're getting there. Yeah, we'll close that loop. Right now we're in the mode where we're going to say, here's all the problems with Java. Even though it's a really good language for some very specific tasks, and that's why it's still around. And we'll get to that. But Microsoft said, hey, we have C#. Brand new language, built from the ground up. We didn't take any inspiration from Java or anything like that. But Microsoft said, hey, our code, our language, is platform independent, just like Java. Now, Java can't accomplish this through a Java virtual machine that they ported to these different things. So they said C# will run on any computer that has the .NET component architecture. Component architecture. Go with that. Just like Java will run on any computer that has a Java virtual machine. The problem is the .NET component architecture is only available on Windows. So Microsoft says, look, C# runs on any computer at all, as long as it's Windows. So it really was still platform dependent, but they made it sound nicer than it was. But C# did have some legitimate advantages over Java. like we just said, Java's performance was never at the level where you can write like AAA video games with it just because you have that middleman. It's not that Java is innately slow. It's that you have this Java virtual machine that's kind of playing handoff between the programming language and the underlying operating system. So instead of the language talking right to the OS, the language is talking to the virtual machine, which then on its behalf talks to the OS. So you kind of have this interpreter in the middle. It's still fast. It's a computer. From our perspective, it's super fast. You write any program in Java, it's going to seem like it runs instantly until you start getting into things that are really starting to push the computation power of your machine. Then you start noticing the cracks in Java's performance. All right, go ahead.
So what do you mean that .NET, like, it doesn't run on Linux? I've downloaded it on Linux.
You've downloaded Mono. So .NET is a proprietary software from Microsoft that they do not, it's not open source. They don't release it. But there's a project for Linux and Mac called Mono, which is their version of .NET. They basically said we looked at all the things .NET's capable of and all the hooks that when you compile a C# program, all the things that it calls in it, and they went and wrote their own version of those. They all had the same name, so when it called those things, it could still connect to it. So I think it's something like 90% of .NET is effectively ported through Project Mono. But that 10% is kind of a big deal because those are the pieces that are very integrated into the Windows operating system. You can't recreate that over on Linux or on Mac. You can try to sort of fake it or whatever, but yeah. So I mean, this is really the equivalent of people kind of making mods for games. They created a mod for Java so that you can, or mod for C# so you could write a C# on other platforms. All right, so we have Java or we have C#. Realistically speaking, let's call these the same language. They're both good. C# is a good language. In fact, well, first of all, anything that's under Microsoft's umbrella doesn't have to be, in many cases, it is as good or even better. It's not, I mean, Microsoft has really good developers working for them. It's not like they have crap. Okay, but because they're Microsoft and because they control this whole ecosystem and they have a very integrated product line where all their stuff talks to their other stuff very easily. So you go to these companies that are Microsoft shops, everything at that company is Microsoft. So they're kind of locked into Microsoft technology. They're using Azure Cloud, they're using .NET, all sorts of things like that. Even if it isn't the best version of that tool, it's the correct version of the tool for them because it's compatible with all their other stuff. Nothing wrong with that. In fact, that exact idea is why Java never took over in that space. Java was never good at having all of their various technologies, the various things that they released to solve different computing problems. They weren't very good at making them all work seamlessly together. Each one was good. They all kind of worked in their own little way, but there wasn't like, oh, have this thing talk to this thing and it's just one line of code. You had to like do this major setup where you might as well have been using a different technology. They just didn't find a way of capitalizing on it. But Java persisted, let's say, for two reasons. One, Google was anti-Microsoft, so they weren't going to use .NET at Google. So they used Java and they used Python. So Java was the main Google programming language for a long time because they weren't going to run Microsoft stuff. And Google's kind of a big company. So that kept Java alive there. But also, any of you do any stock trading or anything like that? Okay. So on your stock trading platform, have you ever used one of these, they're pro day trader investment things where you click the button and this very complex real-time trading platform launches out of your web page. You know what I'm talking about? It's basically a full-fledged, what looks like professional software that launched from a web page. That uses a technology called a Java applet. Java programs, full-fledged compiled programs, high performance that can launch right out of a web browser. That's why Java stuck around. To this day, zillions of dollars per day are made in this world running through professional trading platforms that are written in Java. So those two things kind of kept it alive, but Java's good. It's not like it's this bad language. But C# would have buried them if they didn't have all these other advantages. Okay, now I'm just going to drag this over here for a second. So I want to create another thing. All right, so Java, C# are basically updates to C++. C++ is an update to C. Objective-C was an update to C. It's basically like C++, but does have its own little syntax. Objective-C, what came after Objective-C on Apple's side of things? Yeah, if you're writing an iPhone program today, what Swift? Yep. Any of you ever done anything with Swift? Swift, the language we didn't ask for. I promise you, there was not one person writing software for Apple platforms that said they were unhappy with Objective-C. In fact, that was a high-paying job if you knew Objective-C, because as we talked about earlier, most people were on the Windows platform. Yet Apple has this like presence. So if you could write stuff and I would say a very tiny percentage of developers ever took the time to learn Objective-C. There's a little bit of an initial learning curve, but then you realize that all these languages are the same. But it does have a little bit different look and could be intimidating, whatever. But this was not iPhone developers who said, oh, we need something better than Objective-C. They all liked Objective-C. If you go and look at Swift, Swift looks a lot like Java. Now, who's the competitor to iOS for iPhone stuff? Android. Yeah, Microsoft lost the smartphone war, right? They had Windows CE for a while, and then that died. So you really have two smartphone platforms. You have Android, you have iPhone, iOS. And if you are writing iPhone software in the early days, you used Objective-C. If you were writing Android software in the early days, you were using Java. You're probably still using Java, although there's a language that's been embedded into their thing for a while called Kotlin. It's a pile of crap. But it's fine. It actually is similar to Swift. But in any case, when Swift came out, it looks like Java. What were they trying to do? Look like the language that all of the Android people were writing code in. Come over to the dark side. All you Android developers, come write stuff for iPhone. Oh yeah, you don't want to learn Objective-C? We got a language right here for you. It looks a lot like Java. Very comfortable to switch over. Come make money over on our platform. Swift existed as a money grab to get developers to come over to iOS. And if you were a developer for Android, you would want to jump to iOS. Objective-C was a barrier because it was a language that was intimidating enough to get into that a lot of developers wouldn't have taken the time to go and learn it. And on top of that, to write iPhone applications, you basically had to have a Mac. So those were two barriers that were keeping people from going and writing iPhone apps. But if you look at it from a software developer perspective, there is way, way, way more money to be had on the Apple App Store than it is on the Android App Store. It's not even close. Yeah, so my companies wrote software for both. And I would say iPhone probably for the same software makes 80% more. For the same stuff, it's just it pays better. So in any case, this got some people to come over there, although Swift is a ridiculous language. It's stupid. Like you can name variables with emojis. Again, a feature nobody was asking for. Okay. All right, but Swift is fine. It's there's nothing wrong with it. It's a good language. It just wasn't really necessary. But we can say that Swift, C Sharp, and Java are all kind of on the equal playing field. Those are our three modern, object-oriented, high-level, strongly typed programming languages. Now, all of these languages here, I'm going to label these guys. These are all strongly typed, compiled languages. Okay, strongly typed means that when you create a variable, you have to say, this is the kind of value it was built to hold. Without going too deep into the history and killing a whole bunch of time here, let's just throw Python over here. Python is a loosely typed, although they've added in Python 3, you can make it strongly typed. We'll talk about that. And this is an interpreted language. So what's an interpreted language? Just like it sounds. It's a language where there's a piece of software called an interpreter that during runtime, while your program is running, it takes whatever your Python code is and interprets it to run on the computer that the interpreter was written for. It's no different than if somebody is up somewhere giving a speech in French and you have somebody who's an interpreter who's turning it into English. It's a little bit of a delay there, but quality is fine. With that measurement, Python is actually kind of slow. But again, our computers are so fast, we don't notice. And most of the data science stuff, which is using humongous amounts of data, are using Python, even though that slowness piece should make a difference, but it really doesn't, because in any of the places where it matters, they offload it to like the GPUs and the graphics cards and stuff like that. So they just take the speed requirement off of the language. A language where there's a middleman called an interpreter that when you're running the program, it converts it into low-level code in real time. I'll give us a slide here. We have interpreted versus compiled. Compiled languages use a compiler to convert high-level code, so like Python, Java, C++, whatever, into low-level code, assembly language. So when we looked at Hello World for Linux, let's assume somebody wrote that in C++. Then they ran it through the compiler for the Linux operating system, and it produced that assembly code that is the low-level equivalent of that high-level program. Because ultimately, the low-level language has that one-to-one relationship with the CPU. And then from the low-level language to the machine language, we have something called an assembler that just converts all your system calls there, or like the move command, into the number that represents it. But the heavy lifting came from you writing the 3 or 4 lines of code in a high-level language, which has a one-to-many relationship with the CPU. You write 1 line of code and 30 things are happening on the CPU behind the scenes. Human beings like that power tool. We want to write it with that high-level language, but then we run it through the compiler. The compiler hopefully makes us look better than we were, right? If we wrote inefficient code, it makes it more efficient, but still equivalently like the same logic is there. But this all happens prior to runtime. So when we run the program, its executable is already native for that CPU and operating system. Think faster. Compiled languages are faster. Compiled language also are typically strongly typed languages. Then we have interpreted languages. Use an interpreter to, in real time, translate your high-level code into native code that runs on the OS/CPU, whatever architecture you're targeting. Think slower. Interpreted languages tend to be loosely typed. One is not necessarily better or worse than the other. It comes down to what's the right tool for the job. Video games, almost every single time it's going to be a compiled language because speed becomes an important piece. But a compiled language then comes with the platform dependence piece. If you write a video game and you compiled it for Windows, you might not be able to just recompile that directly and have it run on Mac or have it run on Linux. Mac and Linux have a tool called Wine or WineX that'll allow you to sort of kind of maybe make some games run okay, sort of kind of on those platforms. In fact, an entire platform has been built out of this. How many of you know of or have the Steam Deck? Steam Deck is a Linux computer. The Linux computer that runs WineX, that's why only certain games are compatible with it from Steam. Good.
Technically, it runs something called Proton.
Mhm.
It's their offshoot of Wine.
Yep. Yep. It actually is their closed source version of open source Wine.
Yeah.
Okay, so that's interpreted versus compiled. As a programmer, all these things are important to us, not so much to say, well, this language is better than this language, but when we have a project presented to us, or we are trying to decide what technology should I use to build whatever I'm getting ready to build, we have to pick the right tool for the job. And certain tools are going to pop out as the right tool for the job. For example, if somebody comes up to me and says, hey, we need this software that is going to use AI, I could stop them right there and says, okay, we're going to write it in Python. They use the phrase AI, it will be in Python today. Fast forward 5 years, everybody else will try to jump on the bandwagon, and .NET will have a lot of the PyTorch stuff equivalents for running GPUs and things like that. But for right now, Python's where AI development occurs because that's where data science was. Our modern AI stuff was born out of the tools that data science people have been using for a long time, now that we have large language models that could do a lot more than the older machine learning stuff. All right. So this gives us a little look at the history of some of these programming languages and how we got to where we are today. Trust me, there's some history over here. You've probably heard of a bunch of things before. How many of you have heard of Ajax? React? Angular? We could add more in there, but every one of these, in fact, almost everything you hear about on the interpreted language side, other than Python, and like Google Go is another one of those over there. But all these things, almost every single one of them is a library for JavaScript. The core language is JavaScript, which is actually not related to the Java programming language. JavaScript was the winner from the early days of the internet. JavaScript is the programming language, the interpreted programming language that was embedded in web browsers early on for you to do the logic-based stuff, because HTML is not a programming language. HTML is a data representation language to make things look pretty with pictures and all that stuff. But if you needed to do logic, checking to make sure you filled in your username and password before you send it off to the server, whatever it is, you would use JavaScript to write your logic. It's a programming language like any other programming language. It has facilities for remembering stuff, asking questions, repetition. But a whole bunch of technologies were born out of people wanting to find cooler and cooler things to do on web pages. You know, Ajax came about when you, in the early days, if you were trying to watch your real-time sports scores, you would have had to keep hitting refresh. You know, every minute you hit refresh and see the score update. Okay, Ajax was a thing where we can have a little piece of our screen automatically update. jQuery, which I don't have on here. jQuery is another one that is Ajax done better. jQuery introduced this idea of a document object in HTML pages that you could walk it structurally, where Ajax was kind of a hack. All right, but all these things are just JavaScript libraries that use JavaScript to do other things. Every single one of them. So, and JavaScript's been around since the internet walked out the door. JavaScript's main competitor in the original internet, anybody know what it was? When you originally were making websites and you wanted to have programming logic in your website, you had two choices. You had JavaScript and you had VBScript, a Microsoft product. And they died. VBScript died. Okay, so about that, see, blah, blah. All right, so data types. So really I'm going to talk about C for a second here, since we saw on our chart here that C is at the top. So we can really take anything that a modern computer programmer does and take it back to the C language and see kind of where it was influenced, where it came from. So our data types from C, I'll even throw that out there. But keep in mind that these data types are mostly maintained even in the most modern languages. So what we see on this slide is going to be equivalent to, or very closely equivalent to current stuff. So we had something called a byte, a short, an int, a long, a char, a float, a double, and a Boolean. Nope. Well, there is, but these are, let's call, let me further, these are called primitive data types. Strings exist, they're just objects. Yep. And actually, C, not being an object-oriented language, strings existed in something called a character array. And they had things called C strings. So really what you saw in the C programming language, before C++ came out, you saw a lot of hacks to kind of start making C behave like they wished for this future language to behave. And they were starting to get some stuff in there, which was probably the motivation for getting C++ actually out. All right, so what is a byte? Byte is an 8-bit signed integer. Actually, let me, this is basically all programming languages. Yeah, I mean, there might be like shorts don't exist in Python, but everything else does. It doesn't really matter. This goes through. So shorts hold integers, ints hold integers, longs hold integers. We'll get down to char in a second. So in the C programming language, we had 4 different data types that all held integers. Why? You can store the number 7 inside of a byte. You could store the number 7 inside of a short. You could store the number 7 inside of an int. You could store the number 7 inside of a long. Why do we need to have so many different ways of holding whole numbers? Memory. Why was that a problem? Memory was expensive. Remember that? How many of you know what the Y2K bug is? How many of you were born in 2000?
With it, where everyone's afraid that computers are gonna work.
Yeah, why?
Because they thought that it wouldn't go past 1999 in the date.
Yep. So Y2K bug, early programs use 2-digit dates. Well, 2-digit years. So it was 79 instead of 1979, for example. Which means that 1900 and 2000 look the same. And they thought a bunch of stuff was going to break from sorting and stuff like that. So I remember it was the best New Year's ever, because I'm not into like the ball dropping stuff and things like that. But man, I sat on the couch with maybe a couple of adult beverages and was I was of age. uh, uh, and it was the first time, and even since they literally started at the first place that hit midnight, and they just I think it was somewhere in Australia or New Zealand. I think it's New Zealand, and they just had a camera on like some power station to just see if the thing blew up or something. Nothing happened. But leading up to it, there was all this movement where they were converting all these programs to 4-digit years instead of 2-digit years. And this was because of cost of memory. These older programming languages had the facilities for holding different size data types. And if you were writing this older software, hey, maybe just if it's 1983, you probably assume the software you're writing is going to get replaced by the time 2000 rolls around, right? It's like, we'll just save memory now because it's too expensive. We have to. Or now we have plenty of memory. We'll just use, 4-digit whatever for forever. But this is why those older languages had so many different ways of holding the same kinds of values. So a byte is an 8-bit signed integer. A short is a 16-bit signed integer. An int is a 32-bit signed integer. A long is a 64-bit signed integer. A char is, now this depends, I'm going to stick with the C version of this, is an 8-bit unsigned integer. Now, when you see the word char, what do you think? What do you think that data type is likely to hold?
A single character.
Single character. Well, why is it an 8-bit unsigned integer?
Have the entire string, or not string, the entire log of characters. Characters can, wait, can it be only letters, or can it be just like double quotes or something?
All the symbols.
So that's why it's 8. It has to have all.
What are we using the 8 bits for?
Or to.
I'll tell you, in Java, it's 16 bits instead of 8. Connect that back to something we've already talked about in class. ASCII, Unicode. ASCII is an 8-bit character set. Every 8-bit number maps to a character in the ASCII character set. In Unicode, a 16-bit number maps to one of the 65,536 unique characters in the Unicode character set. Make some sense? That's why that guy is 8 bits. Why is it unsigned? Unsigned means because it supports negative numbers and positive numbers. Well, because the ASCII and the Unicode character set are 0 to 65,535, 0 to 255. We just don't need negative numbers. Nothing prevented them from saying, well, an A is a negative 17. That's just not what it has. Signed means plus or minus. Unsigned means we don't store plus and minus. All right, so let me, I know we actually are farther back from where I said start here last time, but trust me, there's a madness to this. Remember, homework assignment is due Sunday by whatever. Yeah, so do that, do the reading, and we'll keep trucking.